Welcome everyone. Welcome to a new topic, story of atom. As we all know, we are all made of atoms. You are made of atom. I am made of atom. The mobile you are holding is made of atoms. The chair you are sitting is made of atoms. So let's find out what is the story of atom. The first man to say the word atom was this fellow, Democritus. He was from ancient Greece and he said that everything is composed of small, physically but geometrically indivisible particles. He named them atoms from the Greek word atomos, which means that which can't be split. So he said there are infinite number of atoms. Different substances are made up of different kind of atoms. That is, the glass is made of glass atoms. Paper is made of paper atoms. Wood is made of wood atoms. And these atoms differ in size, shape and weight. There is an empty space between the atoms. The atoms are indestructible and they are always in motion. Now, many of them might not hold true right now. Some of them do. But this was the first time when atoms were thought of. Next man in our story is this guy, Aristotle, the student of Plato and the teacher of Alexander the Great. Well, his contribution to the story of atom is that he didn't believe in the theory of atoms. He said that atoms doesn't exist, but all substances are made up of five things: earth, which is cold and dry; water, which is cold and wet; air, which is hot and wet; fire, which is hot and dry; and ether, which is the divine substance that makes up the heavenly spheres and heavenly bodies. As we all know, this doesn't hold true right now, but his legend lived up to 2000 years. For 2000 years, the word atom was lost to the world. And thanks to this gentleman, John Dalton, who brought back the word to the modern lexicon. In the early 1800s, he said that elements are made of extremely small particles and they are called atoms. Atoms cannot be subdivided, created or destroyed. Atoms of a given element are identical in size, mass and other properties. Atoms of different elements combine in simple whole number ratios to form chemical compounds. In chemical reactions, atoms are combined, separated or rearranged. We have progressed in our journey of atoms from this very vantage point. This is the base from which we all started. His model was also called the billiard ball model, as he thought that the atoms are solid, hard spheres like billiard balls. Now, the atomic model has changed, but whenever you see a model of an atom, at the center you always find a hard sphere, something to do with Dalton. In those days, 36 elements were known and Dalton gave symbol for all of them. According to him, if these are the atoms of an element X and these are the atoms of an element Y, then they will combine together in a simple whole number ratio to form such compounds. That was what Dalton's atomic model was. The next man to look into the atom was Joseph John Thomson or J.J. Thomson. At that time, he was working with this tube, which was the Leonard tube or the cathode ray tube. In this tube, metals were given high voltages. A metal cathode was given a high voltage and it used to show a visible beam. The beam was called the cathode ray, or at that time it was called the Leonard ray. Now what he did was he put perpendicular magnetic field and perpendicular electric field in the path of the electron beam. He saw that the beam gets deflected towards the positive charge and away from the negative charge. Also, it is deflected according to the magnetic field strength. This helped him to calculate the charge to mass ratio of the particles, the cathode ray particles. So according to the knowledge he gained from this, in 1897, he said that cathode rays could travel much further through air than expected for an atom-sized particle. Also, these cathode rays were 1000 times lighter than the hydrogen atom, and the mass was same whichever type of atom they came from. That is, he changed the metals, he used different metals as cathodes, and he found the same Q by M. So he said that the rays were composed of very light negatively charged particles which were a universal building block of the atoms. He called his particles corpuscles. Well, you don't hear the name because the later scientist preferred the name electron, which was suggested by the Irish scientist George Johnston Stoney. According to this knowledge, J.J. Thomson gave a new atomic model. As the atoms are neutral, so there must be positive particles in the atom to balance the negative charge. So electrons have so little mass, so that atoms must contain other particles that will account for most of the mass. So he said that there will be a positive charge, a big positive charge on which the negative charges are embedded. He called it the Thomson atomic model or the plum pudding model. According to him, it was a cake or a pudding on which plums were kept. If you don't know what a plum pudding is, you can identify it with the watermelon. The red part is your positive charge and the black seeds are your electrons. For this particular achievement, he received the Nobel Prize in Physics for the year 1906, and he was in his recognition, it was said the great merits of his theoretical and experimental investigations on the conduction of electricity by gases. Now, J.J. Thomson's son George Thomson also received a Nobel Prize. So here is a quiz question for you. Which other parent-child pairs also received Nobel Prizes? Please mention the answers in the comments below. Next fellow who looked into the atom was this guy, the New Zealander who came to England via Canada, Ernest Rutherford. Well, he was the student of J.J. Thomson, and he supervised an experiment to study the atomic structure. The experiment was such a hit that Encyclopedia Britannia considers him to be the greatest experimentalist since Michael Faraday. And he is correctly called the father of nuclear physics. At his suggestions, in 1909, Hans Geiger and Ernest Marsden used fast alpha particles as probes. A narrow beam of these particles was directed at a thin gold foil. I am arriving at the famous gold foil experiment. Now, the Thomson atom, as it was known, could provide a very weak electric field, and it was expected that the alpha particles would go right through the foil with hardly any deflection. Let's see what they observed. This is the Geiger-Marsden experiment, or the Rutherford gold foil experiment as it is popularly known. A radioactive source was emitting the alpha particles, and a gold foil was kept in the path, and a fluorescent screen was placed in front of it in a circular fashion, so that wherever the particles will be hitting, they will measure it. So it was observed that most of the particles were actually not deviated as it was thought of. Few were scattered through large angles, and some were even scattered in the backward direction. Now, the alpha particles are relatively heavy and were fired at high speeds of about 10 to the power of 7 meter per second. So only strong forces could produce such deflections. Also, it indicated that alpha particles went through empty spaces. Rutherford actually remarked it was incredible, as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. That was the impact of that experiment at that time. According to this knowledge, Rutherford came with his planetary atomic model or the Rutherford atomic model. He said that the atom was empty with a central positively charged nucleus where all the mass was concentrated. The light negatively charged electrons revolve around the nucleus just like a revolution of planets around the sun, giving the name planetary atomic model. The radius of the atom was known to be about 10 to the power of minus 10 meters. Using the experimental results of this model, the radius of the nucleus was found to be about 10 to the power of minus 14 meters. Well, Rutherford didn't stop at that. In the mid 1910s, he carried out further studies and was the first to discover proton. He used this name for the hydrogen nucleus. Protons mean first in Greek. Let me tell you, Ernest Rutherford did receive a Nobel Prize, but he didn't receive the Nobel Prize for all this work. He received the Nobel Prize in chemistry for the year 1908 for his investigations into the disintegration of elements and the chemistry of radioactive substances that he had carried out in McGill University, Canada and Cavendish Laboratory, England. All this great work was done after he received the Nobel Prize. Such a great man. And he was in his own humor when he said that the fastest transformation he had ever encountered was his own instant one from physicist to chemist. We have arrived at a juncture where we have to stop today. But the story hasn't ended. It has just taken a small pause. In the next part, we will be looking into the theoretical aspect of the atom and will look after the third particle that will complete the story of our atom. Till then, stay healthy, stay safe. Thank you.